Okay, we're on the YouTube. Yeah. Okay. Inverse f, the inverse of x is denoted as f, that's a minus 1, x. Be sure to remember that this does not mean the reciprocal. Okay? So remember, this is not an exponent. Don't get confused, okay? It doesn't mean we reciprocate. This means something different, which you're right now. The inverse of a function undoes what the original function does. Okay? The inverse of a function reverses the process of that function. So here's an example. If f of x equals 3x minus 4, so notice, first, the BEDMAS order of operations is we multiply x by 3. We do that first. And second, we subtract 4. So the idea of the inverse is to undo all of this. The inverse of a function is this. So notice here the first thing we do is, the last thing we do is subtract 4, but here the first thing we do is add 4. Here the first thing we do is multiply by 3, but here the last thing we do is divide by 3. Okay, so it undoes what the original equation does. If functions are inverses of others, okay, so notice that if f of 1 equals negative 1, then if we put negative 1 into the inverse of f, we'll end up back with positive 1. So notice x1, y negative 1. Here x negative 1 in the inverse gives y a positive 1. So it's reversing. It undoes what the original does. A function f has inverse f1, f minus 1 denoted by this, right? If f of the the inverse of f of b equals a if f of a equals b. All right? So what's happened is your x value becomes your y value, and your y value becomes your x value. In other words, x and y is swapped. Okay? Or switched. Or exchanged. Whatever word you want to use. Okay? The inverse of a relation is obtained, we interchange the x and y, and then we solve for y. I will demonstrate this with examples. The graph of the inverse is a reflection of the graph of the original graph in the y equals x line. So if you recall, the y equals x line is here. So we are now reflecting over the y equals x line. So if f of x contains points such as 1, 1, 10, 10, negative 5, negative 5, then these points would be invariant, because under a switch, that one goes in the domain, right? And that one goes into the range. So under a switch, they would be invariant. They wouldn't change. A function and its inverse are congruent and are symmetric about the y equals x line. In some cases, the inverse... Okay, note that the inverse of a function may not be a function. So its inverse may not be a function, and I'm going to show you how to handle that. If f of x is a one-to-one function, that means for every x value there's only one y value, and for every y value there's only one x value. So in other words, in order to be a one-to-one function, f of x must pass a vertical line test as well as a horizontal line test. So for example, let's look at this parabola, right? It passes the vertical line test. However, it does not pass a horizontal line test. So because of this, the inverse of a parabola will not be a function, right? In order to be a function, it has to pass both the vertical line test and a horizontal line test. So the inverse of y equals x squared will not be a function. However, if you look at a graph such as the cubic graph like this, it passes both the both the vertical line test and the horizontal line test, so the inverse of y equals x cubed is a function. In cases where the inverse is not a function, we sometimes restrict the domain of f of x so that its inverse is a function. And all of this I will demonstrate with examples. So let's start doing. I think the examples are what we really need to help us understand this. So here's a very simple example of a straight line and its inverse. So we want to find the inverse algebraically. So let's do this by, the first thing we're going to do is exchange the x and the y. So we have our function f of x equals 3x plus 5. Because we have to do some algebraic manipulation, we're going to write that as y equals 3x plus 5. So instead of writing f of x, we're going to write y. So just always remember f of x is just another way to write y. We're going to interchange x and y just like this. And then we're going to solve for y. So 3y equals x minus 5, y equals x minus 5 over 3. So now we can write, go back to the original notation, the inverse of f of x equals x minus 5 divided by 3. Now they want us to graph the f of x as well as its inverse and the y equals x line. Okay, so don't forget your arrows here. So we know the y-intercept is 5, so 1, 2, 3, 4, 5. So the slope is 3. For every 1 it goes over, it goes up 3. Every 1 it goes over to the left, it goes down 3. So let's just draw a few of those points, just like that. So this is f of x. Okay. Now, the easiest way to draw the inverse is, well, this point here is negative 1 comma 2. So its inverse will be 2, negative 1, because x and y is swapped. 1, 2, negative 1. That's the inverse of that point. This point is negative 3, negative 4. So the inverse will be negative 4, negative 3. 1, 2, 3, 4, 1, 2, 3. You only need 2 points to draw a line, but let's do one more. This point is 0, 1, 2, 3, 4, 5. So our inverse will be 5, 0. 1, 2, 3, 4, 5, 0. Right? The inverse is 5, 0. So we're in a position to graph this line. This is now the inverse of f of x. And we can draw the y equals x line easy enough. So maybe this isn't a perfect drawing. Oh, maybe it's pretty close to perfect. There is an invariant point there, but because it doesn't land on a line, it would be hard to find. But any point that lies on the y equals x line is invariant. So it's right in there, but that's hard to determine based on this graph. So here's y equals x. Okay, so find the domain of both of them. So let's do f of x. Well, x is an element of real numbers and y is an element of real. It's just a straight line. So, is the inverse a function? Yeah, look, the inverse passes the vertical line test, right? So we know that's a function. Oh, sorry, I forgot to do the domain and range of the inverse. So let's do that right now. So it just so happens the domain becomes the range of our inverse, but it just so happens that they're going to be the same thing. Our domain becomes, our range of our original function f of x becomes the domain of the inverse, which is, everything's going to look very much the same. And the domain of f of x becomes the range of our inverse. And so it looks the same because they're both the same. And that was part C. This was part B. This is part D. F minus 1 of x is a function. So if I were to look at that, it passes the vertical line test. It passes the horizontal line test, right? F of x passes both vertical and horizontal line test. So we know the inverse of f of x is a function. May I explain anything better, or would you like me to elaborate on anything? Let's look at, what else do we have here? Okay, now we have a quadratic equation. The graph is a parabola, so we're going to have some issues with the inverse of a parabola being a function, and we're going to have to restrict the domain of f of x to ensure that the parabola is a function. So this is why this is x. Okay, let's find the inverse algebraically. So we're going to have we have f of x here. So I'm going to write y for now as we're finding the inverse, just so our algebraic manipulations won't be as cumbersome. And so we'll swap the x and the y, because that's what a reflection over the y equals line is. Let's solve for y. So I'm going to add 3 to both sides. divide it by 2, divide both sides by 2.
Please excuse this interruption. At this point, we ask for students with the last name J, K, and L who wish to have a photo retake to make their way down to Titan Hall. Thank you.
We'll take the square root of both sides. And then we'll have y equals negative 1 plus or minus square root of 1/2 times x plus 3. And now we can write f. Do not rationalize the denominator here because this is a little bit different here. We want to keep that fractional value because here we have a horizontal stretch by a factor of 2. So we want that information. So f minus 1 of x equals negative 1 plus or minus square root of 1/2 x plus 3. So let's graph the original function and then we'll graph its inverse as well as the y equals x line. So the vertex here is negative 1 minus 3. When x is 0, y is 2. 2 minus 3 is negative 1. We can reflect over the axis of symmetry and get a third point. Now, when x is 1, when x is 1, we have 2 squared is 4, 2 times 4 is 8, minus 3 is 5. Do a reflection over the axis of symmetry to get the other point. So here is our f of x. Now, the easiest way to do our inverse, we know this point here is negative 1 comma negative 3. So our inverse will be negative 3, negative 1. 1, 2, 3 minus. Just swap the x and y. This point is 0, negative 1. So our inverse will be negative 1, 0. This point is negative 2, negative 1, so our inverse will be negative 1, negative 2. This point is 1, 4, so our inverse will be 4, 1. 1, 2, 3, 4, 1. 1, 4 becomes 4, 1. This is negative 3, 1, 2, 3, positive 4, 1, 2, 3, 4. So our inverse, right, negative 3, comma 4. So our inverse will be 4, negative 3. 1, 2, 3, 4, 1, 2, 3. So now we can draw that guy. Maybe I should draw that guy in red so he sticks out a little bit here. So notice our inverse is not a function. If you notice on f of x, it passes the vertical line test, but f of x does not pass the horizontal line test. When we draw a horizontal line, it hits 2 points. So for that reason, when we do the inverse is not a function. Let's draw our y equals x line. 1, 2, 3, 1, 2, 3. 1, 2, 3, 1, 2. So notice this is just, let's see, maybe this branch of the parabola right here, this branch of the parabola is reflected to be this branch. So the right branch goes to the top, the left branch goes to the bottom. Okay, just an observation. So we want to do the domain and range, so let's do that. This is, I guess this was algebraic, that was A, this is B, this is C. So domain of our original parabola is x such that x is an element of real numbers, and our range is y such that y is greater than or equal to -3. Y is an element of real numbers. F minus 1 of x. Now, the range of the inverse, the range of the original function f of x becomes the domain of the inverse.
Please excuse this interruption. At this point, we'd ask for students with the last name M, N, and O who require a photo retake or missed the first round of pictures to please make their way down to Titan Hall. Thank you.
See, if you look at the inverse, x is greater than or equal to -3. On f of x, it was y that was greater than or equal to 3. Okay, on our range, well, here y can be anything because it's just going to go up forever. So y such that y is an element of real numbers. So the domain of f of x becomes the range of the inverse of f of x. The only thing we want to do now is, we know this is not a function, so let's restrict the domain of f of x. We're going to chop this right in half along the axis of symmetry, so its inverse is a function. So in part D, the inverse is not a function. So in order to make it a function, we restrict the domain of f of x. And how will we do that? We're going to chop it in half so there's only one branch. Remember that the left branch reflects to the bottom branch of the inverse. So if we were to chop this out, we are just going to slice it in half. No, it doesn't matter. We would accept two answers on this one. So if we chop off the left, that will chop off the bottom. So if we only reflect the right branch, we get only the top branch on the inverse, and if we only have the top branch, then the inverse is a function. So we have restriction of domain of it is going to be like this: x such that x is greater than or equal to -1. X is an element of real numbers. Now you could have chopped off the right branch, so this in effect is chopping off the left branch, right? This chops off left branch. Now, and as our young student mentioned, I don't want to mention names on the internet, or we could go x such that x is less than or equal to -1. X is an element of real numbers. We could have done that, but this would have chopped off right branch. So if you chop off the right branch, you'll only be left with the bottom branch. Okay. So this is how we restrict the domain of our original f of x in order for the inverse of f of x to be a function. Can I explain anything better than that? Huh? Any more details you need? You can practice the remaining two. Do you want to do one more? Do you want to do number 3? Huh? Or all of them? Do you want... The hardest one is number 5 because it's that dang reciprocal function. Okay, why don't we do this one? Let's do number 5. Let's find it algebraically, then we'll find it graphically. It's going to be challenging because this is a challenging graph. It's a reciprocal function. So let's do it algebraically. A. Finding inverse algebraically. We'll change f of x to a y. We'll interchange x and y. Now we're going to solve for x and y. So we'll add the two. X plus 2 equals 1 over y plus 3. Now we're going to multiply both sides. We have to get this out of the denominator. So we're going to multiply both sides by y plus 3. So now we have y plus 3 times x plus 2 equals 1. Because this all divides out, right? So now we have to solve for y. So we're going to divide both sides by x plus 2. So we have y plus 3 equals 1 over x plus 2. Y equals 1 over x plus 2 minus 3. So the inverse is equal to 1 over x plus 2 minus 3. That's the inverse algebraically. Let's graph this guy. I'm going to graph y equals 1 over x first, and then we're going to move it left and down 2. Left 3, down 2, right? So the original graph is here. Hopefully you feel comfortable with that by now. You only need those points. I'm just going to graph using transformations. Graph number 1 is y equals 1 over x. Let's see. Just to help us for reference purposes. Graph number 1 is y equals 1 over x. Graph number 2 will be 1 over x plus 3 minus 2. I'm going to do that in red so it stands out. So we go left 3, down 2. Let's do the bottom one. Left 3. 1, 2, 3, down 2. 1, 2. 1, 2, 3, down 2. 1, 2. Nope, I think I did something wrong. This is no good. Left 2, left 3, down 2. 1, 2, 3. That one's okay. Let's do this guy. 1, 2, 3, 1, 2. 1, 2, 3, 1, 2. All right. Can you see, if you recall, this is x equals 0 is our axis, is our asymptote. X equals 0 is our asymptote on y equals 1 over x. What is our asymptote on y equals 1 over x plus 3 minus 2? X equals negative 3 is an asymptote, right? Right? Because you can't divide by, x cannot be negative 3, and if x is negative 3, your denominator is 0. So x cannot be negative 3. So you're going to have an asymptote there. Now, the asymptote on y equals x is y equals 0. Our new asymptote is y equals negative 2. So we're going to have a horizontal asymptote of y cannot be negative 2. Okay, so the lower branch on y equals 1 over x plus 3 plus 2 is here. So let's do this guy. Left 3, down 2. 1, 2, 3, 1, 2. This is going to be really hard. The inverse will be really hard to draw, but we'll be okay. 1, 2, 3, down 2. 1, 2, 3, down 2. Now, if you're able to draw 1 over x plus 3 plus 2 immediately, you're more than welcome to do that because you can pick off the asymptotes.
Good morning, York Mills. Today is October 16th and a day 2 on your time table. Please
Can we finish this tomorrow?